Like this should be better.
Mm-hmm.
So today we're gonna cover actually 3.1 and 3.2. I'm gonna fix this a bit later. And if you remember right, last class we discovered how derivatives could be useful in terms of determining direction of a movement, sign of the speed and acceleration. Do you recall that?
Yeah.
So yes, and today, in fact, we're going to continue investigate problems involving derivatives. So let's move to the, oh, for some reason outcomes are not visualizing here. But as a result of today's class, we're going to look into problems involving rates of change, and we're gonna solve them using derivatives. Also, we're gonna take a look into advanced graph sketching. So before that, you, for example, to sketch a vertex, you were making a perfect square of a quadratic function. Do you recall that? Or
Uh,
simply using your formula minus b divided by 2a, I believe.
I don't
That was the method you showed me that you said you studied
to
to
find what?
find vertex of a
Oh
quadratic.
yeah.
So yeah, and today we're going to look into more advanced methods of sketching the graph to find the vertex, or in other words, to find extremum of the function.
What is
And
it?
it's called extremum, and we're gonna take a
Okay.
look into it. So so extreme value of a function. So let's start off with where we ended in the last class. A few more examples to solve. So first, can you read this for me, Alan?
Uh,
Example 3, what
connecting
is given?
connecting motion to displacement, velocity, and acceleration. The position of an object moving at a line is given by s of t, where s is in meters and t is in seconds. Determine the velocity and acceleration of the object at t equals 2. Oh, okay.
So let's do it step by step, right?
So first,
Um,
we
would you like to say the solution?
yeah.
Okay,
So s is the displacement. To find velocity, we have to take the derivative of that.
great.
Take the derivative, that would be 12t. Oh yeah, 12t subtract 3t2.
A square.
Yeah, sorry. And then
Great.
we plug, if we want to find in the velocity, we just plug 2 in for t,
Okay, we say t equals 2,
and then
and we evaluate it as
yeah,
prime of t when t equals 2.
and then we get 24 subtract 12. Yeah. And then we get 12.
So
So
copy
velo-
it into your copybook.
oh, yeah.
So here you see Leibniz notation and prime notation. Let me know once you finish.
Okay.
You got it?
No, I have to write the question note.
Okay.
Is there like
Just how would you write this in short notation? In my copybook, I would write question A, and what is asked? Determine the velocity and acceleration of the object at t equals 2. So I would say velocity at t equals 2, question mark, and acceleration at t equals 2, question mark.
determine the velocity and
Then I would say that function of velocity equals derivative of a function of displacement by time, right?
Hmm.
Oh, we have a new guest. Keep writing. Hello, Abdullah. Can you hear us? You can type in the chat. Or hello, Abdullah. Okay,
is
let's
it is it meters per second?
velocity.
Yeah, yeah.
Yes,
Okay.
absolutely right. Meters per second.
Okay. And
So you write it like this, right? Function of time. Oh, we have two more guests.
really?
Hoda, can you hear us?
Yes.
Welcome to the class. Nice to meet you.
Nice to meet you too.
So my name is Ilya, and today we're discovering properties of derivatives, how we can apply them in problem solving. Are you familiar with limits and derivatives?
I already took this at school 3.1.
Mm-hmm.
Yeah, so I'm familiar with it.
So great, but revision is never too bad, right?
Yeah.
So Ahmad, hello. Feel free to ask any questions or type in a chat. So Alan, let's continue. Where you stopped?
I already went on and I did acceleration.
Was already?
Yeah.
Did you wrote it in terms of Leibniz notation or prime notation?
The first one.
Okay. So can you say
Okay.
me what is your solution for acceleration in this case?
A of t equals
Wait a second. Yes, A of t.
d over dt.
Yep.
Times or like s prime of t. Yeah, like that. Equals 12 subtract 6t.
You don't really want to mix up notations here. So what I would do in your place, remember, way we denoted second derivative would be to note square in front of d in the numerator and square in front of t in the denominator. So we had square in front of a variable, and we had square in front of the delta in the numerator.
I forgot I had to square it.
So this is the way you would represent second derivative in Leibniz notation. Is it clear?
Yeah.
Great. So what's the solution?
12 subtract 6t.
Sorry, no, let's go make a step back. Tell me the derivative of, tell me the second derivative of a function of a displacement, because this is our initial function right here. Everybody who's new. Oh, hi, Ahmed. So here is a function of the displacement in this case, and we need to evaluate second derivative. How would you do it?
Well, I took the derivative of the velocity, and then I took,
Okay, so you say that now we take derivative of function of velocity here, right? But now we take derivative one time, right? So
Yeah.
no more root, oh, no more square here.
Sorry. I did, I took the prime of S, T.
Yes, as we discussed, you shouldn't mix up prime notation with Leibniz notation. I see. So to represent second derivative in Leibniz notation, you would have to put two dash lines here, and that's it. If you would like to represent second derivative in terms of Leibniz notation, when you have delta over delta t, it would mean that you just need to square it up.
Okay. So if I add the double hashes, I remove the squared, or do I leave the squared too?
So if you add double hashes, you remove this and add them, because now it's not Leibniz notation, now it's prime notation. In
Oh,
this way, first derivative of function of a speed would have one dash.
Okay.
So now we take derivative of function of velocity, so it would be 12t subtract 3t squared, as we found in the previous step right here. This is our derivative of function of displacement, which is equivalent to function of speed. And now only last step to differentiate it one more time. Now we'll get 12 subtract 6t. Remember to use power rule.
Mm-hmm.
Now we substitute t for 2 because we're interested in an acceleration at point 2. So we get 12 subtract 12 equals 0.
Okay.
So it means that at point of time 2, acceleration of an object equals 0.
Is it meters per second squared?
Exactly. So remember, velocity is described in meters per second, and acceleration described in meters per second squared.
Okay. I write ms squared.
Oh yeah, sorry, it's wrong. Did you copy it already?
Wait, so
So what about our guest? Would you like to copy it into your copybooks, or you would like to just observe today? Hoda, what about you? Ahmad?
if you add the double hashes right here, then you don't have to add the d over dt.
So let me clarify it. Just d over dt is first derivative.
Okay.
If you would like to state that you take second derivative of function of displacement, you gotta choose which notation you prefer.
Okay.
One of them is Leibniz notation, with second derivative would be squared here. This is Leibniz notation. And this is prime notation, very different notation.
Okay.
It's as if you would use alphabet from two different languages in the same sentence.
So can I do that for the first step too?
For the instead of writing d over dt here,
Yeah. Can I
you
just
can
put?
you can just put one dash here.
Oh, okay. I prefer that.
That's simplified.
Okay.
So Yusuf is finally here.
Hi, sorry for being late.
Oh, no forgiveness for you, Yusuf.
I
I'm
was-
disappointed.
I'm-
But you didn't miss a lot. We just they made a first step. You can review it in the recording of this class, or right now, just simply understand that here we determine the velocity and acceleration of an object at point of time 2 seconds. And if you recall from the last class, we discovered that velocity is first derivative of function of displacement, which is given here.
Yeah.
And acceleration is second derivative of function of displacement. So you just simply need to evaluate first derivative at point of time 2 seconds and second derivative at point of time 2 seconds.
Okay. Yeah.
I hope you remember it.
Yeah, I remember. Yeah.
Okay. No worries, Ahmad. If your mic is not working, just let me know. Can I continue? Did you copy it? Beautiful. Let's go on. So, next step for us. B. Here is solution for A, just in case.
Okay.
So, let's check. Indeed, velocity was 12 and acceleration 0. So we are correct. So, question B. At what time is the object at rest? So what do we know about resting? It means we're not moving anywhere.
Velocity is 0.
Great. So let's say object would be at rest when function of velocity by time would equal 0, right?
Mhm.
So now we just need to write down the function of velocity, which is, we know, the first derivative of function of displacement, and write it, find solutions when it's equal to 0. Simple as that. So function would be 12t subtract 3t squared. This is already our derivative. Now we say it's equal to 0. And now we treat it as normal quadratic function where we are looking for the roots of the equation. My favorite way to solve this, I would list it here. First thing what I would do, I would factorize it to break it into product. Because when we have product and we need to find when product equals 0, it simplifies our life a lot. So here I see that 3 times t would be my common factor for both components, right? For both terms in this equation. 3 times t times 4 subtract t equals 0. Now I just need to find at what value is this. This is true, right? And it's not so hard, because if 0 multiplied by anything, it's equals 0. So I have two solutions, 3t equals 0, or 4 subtract t equals 0. So t1 would be 0, and time 2 would be 4. Did you get it?
4. Yeah, right. I think so.
Yeah, I got it too.
Let me just write it down.
Guys in the chat, how are you doing? And ladies?
Oh yeah, I got it.
So now we can say that object is at rest at start of its movement, right? At the beginning, we don't have any velocity. And also at point of time 4 seconds, we don't have any velocity. What another interesting thing should we state? That if we would make a tangent line to this curve at the point where velocity equals 0, if this curve describes displacement, It means that the tangent line passes at 90 degree to this curve. So, or parallel to x-axis.
Mm-hmm.
You got it? Did you copy it into your book?
Yeah.
Except of this, this is just a short note remark.
I got it.
Great.
Just 1 second. I almost got it.
Hurry up, use it.
Okay, I got it now.
Great. So let me clear it. And here's solution B. And as you see, they are correct. Agree?
Yep.
Yep.
C. In which direction is the object moving at time equals 5? Interesting. Does anybody knows the answer?
Positive. Wait, no, negative.
Why?
Well, because if the object is at rest at 4, that means it stopped moving, so then it has to come back down if it's a parabola.
But we don't know yet how this graph looks. You see, we have third
Oh,
power,
geez, the
so
original
it
parabola.
wouldn't be parabola. We have third power in here.
Well, if you plug it into the velocity, you'll get-
Oh, yeah, good. Velocity is in fact quadratic function with second power. It would be 12t subtract 3t squared. And this is parabola that facing
Yeah.
downwards. Right?
Yeah.
But it's not really what we're looking at. Remember, direction of movement determined by the sign of the derivative. Because let's remember, if derivative of the function of displacement, which is speed, has negative sign, it means object moving to the left or backwards, right?
Mhm.
So what we gotta find here is what sign does the function of velocity has at moment of time equals 5. So how would we do it? We would write down the function of velocity. Find its value when t equals 5. It would be 60 subtract 25 times 3, 75 equals negative 15. And now we look here and we see that the sign is negative. So it would mean that the velocity directing backwards or to the left if we're talking about linear movement. You got it?
Yeah.
So what direction is the object moving? Left or right, up or down?
Left.
Okay, perfect. Everybody else, any questions?
I don't have any question now.
Okay, let's move on. Let's see. C. So answer would be movement in the negative direction, because when we say that object is moving in a line, we don't actually know where this line facing. Okay. Because if you draw a line in a 3-dimensional space, it could look anywhere, right? Up or down, left or right, and an angle.
Well, that's actually right, yeah.
So no matter where this line facing, we have two directions, positive and negative. You see? So in this case, when we don't know where we're actually going, up or down, left or right, the correct way would be to say that object is moving in negative direction. You see, no matter where this line is pointing, we still have positive and negative direction. Is it clear?
Yeah.
When is the object moving in a positive direction? I think right now we can pretty confidently say
From
the
0 to
solution.
4.
To solve it, I would plot this graph first. Let it be something like this. I'm not exactly sure where it passes or not, the x coordinate, but I know one thing for sure, that at time 2, velocity of an object equals 0. So it reaches its greatest distance from starting point and turns backward, because parabola
Mhm.
this would be parabola of function of velocity, right? Because function of displacement has different appearance. So when is the object moving in the positive direction?
From 0 to 4.
Wait, yeah, from 0 to 4? From
Yeah.
0 to 2, I would say.
Well, it's still moving positive in 3 and 4.
Why would you say so?
Well,
Because we just determined that at 5 it moves backwards.
well, yeah, if you plug in 3 to the velocity formula, you're still gonna get a positive number. And 4, you'll get 0, but 0 is still positive.
So let's check it. 12t subtract 3t squared. And we look at the moment of time 3.
Yeah.
So 36 subtract 27. 927 would be positive, right? So what are we missing here? But we indeed find that at moment of time 2, object is has 0 velocity.
No, that was acceleration. It has.
Oh yeah, 0 acceleration and 12 velocity.
Mm,
Oh, so acceleration after this point changes to the negative, right? But not the velocity.
uh-huh.
So actually, to determine when the object moving in a positive direction, you would have to plot the function of displacement, for example. And then on the graph, you can see when the distance is increasing and when it's decreasing. So to find when object moving in positive direction, we need to find when direction changes, right? And when direction changes, when the sign of derivative changes, right? So what would be derivative of function of displacement?
The velocity one.
Exactly. So now we take the function of the velocity, and now we need to find when it equals 0, because when it equals 0, it means velocity was, for example, positive before this moment. And if we reach 0, it means we begin to decelerate, and then eventually we turned around.
Mhm.
So what we need to do in this case, knowing all that, we just have to take the function of velocity and find when it's equals 0. And we already did it, right? At what time object is at rest? You always look at the chain in this type of tasks. They're asking you to find and determine the velocity at time of 2 or at what time object at rest, not just because they want to. Because you see, everything is consequent of the previous one.
Mhm.
So now we say Vt equals 0, and we found that velocity equals 0 at time of 0 and 4. So we have two values of x, or time.
Yeah.
0 or 4. So, but at moment of time 0, it's obvious that we don't have any speed. But in at the moment 4 seconds, something happened and velocity turned into 0 again. So it means we were going into positive direction from 0 to 4. And you remember at moment of time 5, we already have negative direction.
Yeah.
So 4 would be maximum.
Yeah.
So at point of time 4, our function also reaches, function of displacement, reaches its greatest value, because after that we turn backwards, right? So we basically covered two questions in one. When the object moving in positive direction from 0 to 4,
Yeah.
at what time object reaches greatest distance from starting point? At 0 to 4,
Mhm.
at moment 4.
Yeah.
When is the so let's see what they suggest us in solution. So here is the reasoning they provide. So basically, yes, another way to solve it, the object moves in the positive direction when velocity is still positive, you see? That's basically another way to approach this. In this case, you would write down the equation of velocity divided by factor -3, and that's where your equality sign changes direction. Are you familiar with that?
Yeah.
That if you divide left-hand side or right-hand side by negative number, equality sign changes direction.
Mhm.
So now again, you're gonna see that this equation satisfies for t equals 0 and 4. You have any questions about this approach?
No.
Take your time. So do you understand the reasoning about how to determine when this function is positive or negative?
Not really.
So you gotta look at sign in front of the components. For example, here t has positive sign, right? So it means if we take time greater than 0, this component always gonna be positive, right? Makes sense? Because no matter what positive number you take, this is going to be positive. Yeah. On the other hand, if you take t less than 0, this would be negative. Make sense?
Yeah.
But now we'll take a look at t minus 4, and t minus 4 would be positive when t greater than 4, and would be negative when t less than 4. Do you see this? Guys?
Yeah.
So now let's take a look at example like this. So basically what we see here in case 1, t greater than 0, while t minus 4 less than 0. It means t is somewhere in a range from 0
Can it
to
not be
4.
t equal, greater than or equal to? Why is it just greater then?
Pardon?
Why is it not greater than or equal to? Why is it just greater than and less than?
Because it would be equal to 0, then the whole equation would be equal to 0. While we are asked when direction is positive. We're specifically asked about it here, you see?
Okay.
It doesn't says when direction is positive or object in a rest, because when it's equal 0, it means object at rest.
Okay.
And on the graph, you would mark this area like this. And remember that, oh, actually not like this, but you see the whole parabola is in this range. But keep in mind that points 0 and 4 are not included. Because velocity equals 0 is not the same as velocity is positive. Any questions about this?
No.
No.
You're confident?
Yeah.
Yeah.
Anybody else? Okay. So let's speed up a little bit. What is the time right now? 7:47. Okay. Let's make let's finish this example and then make a quick break, okay?
Okay.
So when does the object return to its initial position?
Okay.
So how would you solve this?
You could do guess and check, but that's not ideal.
Why guess and check? Let's just solve it. Because what it says, object return to its initial position. It means distance from initial position equals 0, right?
Yeah.
So we simply write function of displacement by time equals 6t squared minus t to the third power equals 0, right? We also would like to say that we are looking for solutions for time greater or equal to 0, right?
Yeah.
But now let's think, what would we include t equals 0?
No,
Why?
it would equal 0.
No. Based on the question, why we don't include t equals 0?
That rest. Wait.
So let's read it together.
Um,
When does the object return to its initial position? It means that we
Well-
are not interested.
Because it starts at 0, actually.
Yes. So we're not interested in the starting point because at the starting point, we already know that distance equals 0. So
Hmm.
our solution would lay in the range t greater than 0.
Yeah.
So now I would solve this in a similar way. I would factorize it. Greatest common factor here is t squared. And now we have two solutions again.
So it's gonna be t equals 0. Or
And
6.
6. But we said that we're not interested in t equals 0, so we cross it out.
That. So
Or
then,
you can say next step t1 equals 0, line not in the range. Let me know once you copied this.
I got it.
I got it.
Okay, what about our guests today? I hope not one-time guests. Ahmad, Hoda, how are you doing?
Sir, I have a question.
Yes, sure, go ahead.
I have a homework question from 3.3. Is it possible if you can help me with it?
3.3 in the same textbook?
Yeah.
We would have to do it at the end of the class, okay?
Okay, thank you so much.
No worries. Okay, guys, let's move on. Let's see if we're correct. Exactly, look, we did everything right.
Hmm.
Did you memorize the approach, how we solved it?
I wrote it down.
You wrote it down, right?
Yeah.
Great. So now let's make a 5 minutes break. You're fine with it? Or 10 minutes break?
Yeah.
10 minutes?
Yeah.
Okay. Now we can, I can help Hoda while there's 10 minutes to take a look at the exercises. And everybody else could take a rest. So Hoda, let me know what's the pages.
It's page 146, question 11.
Let me see. Oh, page
146.
yes, exercise 3.3.
Yeah.
4.146.
Yep.
Which number?
Number 11.
Number 11. A
Yeah.
cylindrical shaped tin can must have a capacity of 1,000 cubic centimeters. Determine the dimensions that require the minimum amount of tin for the can. Assume no waste material. According to the marketing department, the smallest can that the market will accept has a diameter of 6 centimeters and a height of 4 centimeters. So Mhm. Okay, so have you got any ideas about this?
I tried, but I couldn't do it. So yeah,
What have you wrote?
I wrote like the I wrote the height of the cylinder and the diameter. Not much.
So can you write me an equation of volume? How would you determine the volume?
Mm. So the volume. Where am I supposed to write it?
You can write it in your copybook
Oh,
and just say it to me.
So the volume is V equal to pi R square H.
You said page 146, right?
Yeah.
Mm-hmm. I see this is extra assignment, right? In your home task.
Yeah.
So let me just go back to it. Shape Tinkin must have a capacity. So let me share it. Can you see it now? Let's try to solve it together. A cylindrical shaped tin must have a capacity of 1,000 cubic centimeters, right? So we say volume should equal to 1,000, right? Determine the dimension that required the minimum amount of tin for the can to maintain such a volume. So now let's take a look at the can. How is it built? It's basically a cylinder, right? So and we also know the smallest can that the market will accept has diameter of 6 centimeters. So diameter here, right? 6 centimeters. And a height of 4 centimeters. 4 centimeters. They mentioned that required the minimum amount of tin for the can. So basically, how can we express amount of material that is used for this tin? How would you express it?
Sorry, can you say that again?
How would you represent amount of tin that is required for the can? You see, here they say that we need to determine the dimensions when the amount of tin is the smallest possible, but we still maintain volume.
Yeah. I'm not sure.
So, and one way is to use formula for surface area, because if we're talking about material that we are making out, right, it's gonna be some wall, let's say 1 centimeter thick, right?
Yeah.
No, for example, the or cup. If we're talking about can, basically we're talking about some canister that can contain something in it, right? And how would you do it? You would roll sheets of metal. And if you unroll the cylinder, it's going to be like rectangular and two circles, right? Make sense?
Yeah.
So now you can express amount of material as a surface that is that you basically have here. So what would be the surface? For cylinder, to evaluate the surface, it would be two surfaces of circles, or PR a square, right? Am I correct? Is this the surface of a square?
Yeah.
Great. So we need two of those, plus surface of this rectangle that we have here. Surface of this rectangle would be its widths over lengths, or widths by lengths, right? So here we know widths would be the heights of the cylinder, and widths and the lengths would be the length of a circle, basically, or 2PR. So you would say width equals height and length equals 2PR. You got this?
Yeah.
So now you express amount of material as surface area of your can, right? And let's take a look at what you have here. So surface of the cylinder would be 2PR a square, two circles, right? Plus 2PR times height. Because this is surface of a rectangle. You get it?
Yeah.
This is the length and this is the width.
Okay.
Now you have formula for surface that depends on radius and height of a cylinder. Now we already have some dimensions that we can link together. What else do they ask us for? They ask us for the volume to be 1000. So now let's write down the formula for volume. How would we measure the volume of the cylinder?
We do volume by R square and H.
Okay, pi r square times h.
Yeah.
So pi r squared times h. Yep, that's correct. And now you see we have two equations that both depend on r and h. You see that?
Yeah.
So now you need to find what are these dimensions when s is the smallest possible, but at the same time it satisfies this equation to be equal to 1000. Make sense?
Yeah.
Here you also know that minimum dimension that they will accept is 4 in height and 6 in diameter. But remember, you have radius here. So you would say your radius equals diameter divided in half, or 6 divided in half, or equals 3. So you're going to use 3 in your calculations.
Why did we divide it by 2?
You divide it by 2 because in this formula you use radius, and here you're giving with diameter of the cylinder, and diameter is 2 times the radius.
Okay. So we divided it because if we want to find the radius, right?
We divide it because we use radius here, because in
Oh.
fact you can rewrite these formulas using diameter, and you wouldn't have to divide by 2. And I think that's even better because at the end you're asked to find the diameter and the height, right? So let's do it this way. Instead of writing r here, pr is 2pr times h, you would just write p times d, because 2r is already diameter. P times d times h. Because 2pr equals p times d. You got it?
Yeah.
2pr is square. We're gonna change for d square, d squared divided by 4, or I would prefer d over 2 to the second power. And then you can open the brackets here, you can simplify it, you can say this is equal to d squared over 4 simplified with this factor, you would get 2. As a result, it's going to be p times d squared over 2. And this would be your two final equations that you gotta use. Gonna bring them out here. I wouldn't be able to solve this whole equation for you right now, okay? I simply not allowed to do that as soon as it's your home assignment, but I gave you a lot to think about here. You see, at least now you have some equation to work with. And remember what you covered in that class. Did you learn about extremum of the function?
We didn't do like this example or similar. That has to do with cylinder.
Yes, but what method did you use to solve other problems?
Like, it depends on the question. So we did like the one that you cut the rectangles. Yeah, and
So I would remind you that in this chapter, let's scroll a little bit up. Optimization problem, right? And what do we use for optimization problem? Here's basically what you need to know. And one thing I see right away, determine the domain of the function to be optimized using the information given in the problem. And now let's take a look how we can specify the domain in this case. Because I'm pretty sure you haven't done this when you first tried this task, right?
yeah.
Just follow the procedures, algorithm. They are here for a reason. 1 for 6. So 11, where it says that we'll accept diameter 6 and height of 4. It's the smallest. So what it means that the diameter for us could be greater than 6 or equal to 6, while height could be greater or equal to 4 centimeters. And now you found the domain of this function. Here you can rewrite this as d squared over 4. Please copy this into your textbook. Let me change the color. Maybe it would be better. I don't know. I can't. Hoda, you got it?
Yeah, thank you.
From this moment, it's not much left for you to do. Just remember, what technique did you use? I'm pretty sure you discovered the minimum and maximum values of functions. Do you recall that?
Yeah, we did that.
So use that. I'm pretty sure that's what you need in this problem, because it's optimization problem. In optimization problem, usually we're looking for maximum or minimum values.
Okay.
Here, this function tells you, in this function, you gotta look for minimum amount of tin. Because remember, we connected amount of tin with the surface area. How much surface area do we need to cover with tin? So find minimum of this function with these variables. And make sure that with those values of variable, you are satisfying this equation that your volume is 1000.
Okay.
I hope I helped you. One more interesting thing to note in this task is that take a look at that, how your velocity, how your volume depends on height and diameter. Are you here?
Yeah.
Yeah. So look, take a look at this. You see that your height has no power, or power equals to 1.
Yeah.
While diameter has basically second power in it. So it means if diameter and height are the same, diameter brings more impact into the final volume.
Okay.
So you can, and if you look here, diameter also gives the greatest impact into surface space.
Okay, thank you.
Oh, Hoda, are you still here?
Yes.
I have one more advice for you. What can help you to solve this problem? Just use software like what it's called for plotting the graph. Anyone you know? Are you
What?
use this software to plot the graph of a function.
Okay.
Because let me switch back to this problem. While we're still waiting for our friends, why not to help our guests? So we determined the function for volume, right? Is that correct?
Yeah.
So function for volume would be P times D squared over 4 times height, right? Am I correct?
Yeah.
And we also know that it equals to 1000. And if you move everything to one side of it, you're gonna get pretty straightforward equation. PD square over 4 times h subtract 1000 equals 0. Here you have equation with two variables, right?
Yeah.
Diameter and height. So we gotta decide which one do we want to lock. Am I correct?
Can
And
you say that again?
we have to decide which of these variables do we need to lock in order to build a graph based only on one variable, because you don't know yet how to build a graph based on two variables, right?
Yeah.
So what I would do in your case, I would refer to my observation on that, what affects my volume and surface area most. And diameter in this case affects it in the most dramatic way, isn't it?
Yeah.
So I would log diameter to its minimum size, and it's 6 centimeters. I would say that diameter equals 6, and I would plot a graph for height in this case. And it would be a pretty straightforward linear function for you here. Do you see it?
Yeah.
Because you don't have the second power anymore with the variable. This turns into 6 square. Am I right?
Yep.
And now you have only height in this equation. You just plot the graph for height, and at any point of this graph, basically what's going to happen? So it's going to be a function of volume based on height, right?
Yeah. But don't we have to find like the minimum?
Yes, and now you're going to take a look at the other function for surface area. Two surfaces of squares, of circles, two surfaces of circles plus surface of rectangle. And it also depends on same variables. But now you would like to find the minimum of this function. Once you found the minimum of this function, for example, again, you can make this function based on h if you fix the diameter. And then you compare the result if h from here satisfies this equation.
Okay, thank you.
I hope it helps you. Where is everyone?
I'm here.
I'm here.
Please say next time when you come back.
Oh, sorry.
So let's move on with our example. We are running out of time. Analyzing motion under gravity near the surface of Earth. A baseball is hit vertically upward. The position function s of t in meters of the ball above the ground is s of t equals subtract negative 5 times t squared plus 30t plus 1, where t is in seconds. A, determine the maximum height reached by the ball. B, determine the velocity of the ball when it is caught 1 meter above the ground. Here's the solution. But unfortunately, I don't have time to explain you all of it. But in first one, determine the maximum height reached by the ball. It means derivative should equal 0. It's the moment in time when ball changes direction, right?
Yep.
If it was launched upwards initially. And we see that function of displacement would be hyperbola, upside down hyperbola.
Mhm. Can you show the solution?
Write it down and let me know once you wrote it down.
How do we know t equals 0?
We don't know t equals 0.
Versus vt equals 0, we obtain t equals 0.
We obtain t equals 3.
Oh, 3, sorry. 3. How do we know that?
So you would solve v of t equals 0.
Okay.
This is your v of t. V of t equals minus 10 times t plus 30. Now you solve it for v of t equals 0.
Okay.
That's what it says, solving for v of t equals 0. Here you find that t equals 30 minus divided by minus 10. And what is it equal to?
T equals 3.
Great.
And then
We substitute it into initial function of displacement. Again, into initial function of displacement. Sorry, it's here.
Yeah, and then
Do you understand it?
yeah.
Question B. Determine the velocity of the ball when it is caught 1 meter above the ground. So what does it mean? What it's gonna be 1 meter above the ground at the start and at the end of its flight, because we launch it from 1 meter above the ground and we catch it 1 meter above the ground, right? Do you agree with me?
Yeah.
And why do I say that we catch it, throw it 1 meter above the ground? Because when I substitute distance equals 1 into my initial equation,
Mhm.
I just have to solve it for quadratic equation. You see? Like we did in previous step. And when I find those values of t, it means my function takes value 1 in those 2 points, right?
Wait, what is the question again? For the question B? What was it asking us to find? Can you go back a slide? Okay. Let's see a picture of that. Okay, you go back to the solution.
So now you solve it for v of t, s of t equals 1, you see? And you find that this displacement would be equal to 1 in 2 moments of time, at the beginning and at the end. And in fact, you can see this by looking at the initial equation of displacement. Do you remember what this one stands for? This term with no variable in it. It's vertical displacement in parabola. Do you remember?
One, the
1 plus 1 in this case is vertical displacement
Yeah.
along vertical axis upwards. Make sense?
wait, can I ask how you got from the first step to the second step in the solving it?
B?
Yeah.
So let's discover it. We substituted s of t equals 1. Is it clear why we have 1 here?
Yeah.
Now we just rewrite our initial equation, right?
Yep.
Next step would be move everything to one side. In this case, it's easier to move 1 from left-hand side to right-hand side. So you get 0 minus 5t squared plus 30t plus 1 subtract 1. We
Oh,
simplify it and we get minus 5t. Now we factorize it, t minus 6.
okay. And then use math subtract to minus 5 t. You get t minus 6. And then you get 0 equals negative, oh, sorry, 0 equals 0, t equals 0, and t equals 6.
Yes.
And then determine the velocity of the ball when it's caught 1 meter above the ground.
Yes.
We
So
didn't find-
these two t's are moments of time when ball is 1 meter above the ground. For t equals 0 would be a moment of time when ball was launched into the air, right?
This is determine the velocity when the ball's caught.
Yes. So ball would be caught at moment of time t equals 6. Right?
Oh, if we plug in t equals 6 into the equation, we get,
For velocity.
okay,
And how would we find the equation of velocity?
the first derivative of the,
Exactly, of equation of displacement. And in this case, it would be minus 10 t plus 30. We substitute t equals 6 in here. And we get minus 60 plus 30 equals negative 30. So what does it mean? That ball has speed of 30 meters per second towards the ground. Or in negative direction.
it's moving down 30 meters per second.
Yes. Or moving 30 meters per second in negative direction.
Yeah.
Is it clear for everybody?
The 0, do we use 0 as well, or can we cancel that out? For t equals 0 and t equals 6? Is 0 still
We
a
cancel it out at this step.
okay, we don't, okay,
T equals 0 is the time at which the ball leaves the bed.
okay.
Can I clear it now?
Yeah.
So here's solution equals 6, negative 30 meters per second. And here you can see that we found that extreme value of this function. It's the moment of time when ball changes its direction, or we defined it as equals 3, right?
Mhm.
And when time equals 3, displacement equals 46. And that's the coordinates of this point.
Mhm.
Did you get it?
Yeah.
Here's the summary. Pretty much everything that we covered in unit 3.1.
Okay.
You're gonna review it in lecture notes, okay? In Google Drive. Now we're gonna touch up maximum and minimum on interval, extreme values. This is what we see in this case. So this point would be the extreme value of function of displacement. In this case, it's maximum value when function reaches its maximum. But for example, if we had parabola like this, and we find point on the bottom of this curve, it would be minimum. You got it?
Mhm. Yeah.
Let's take a look. So now we're just gonna do one example. There's 2 times they ask you to do this. We're gonna do it once, and we're gonna end our class at this moment. The purpose of this investigation is to determine how the derivative can be used to determine the maximum largest value or the minimum smallest value of a function on a given interval. Together, these are called the absolute extreme on an interval. Any questions?
No.
Absolute extrema. For each of the following functions, determined that by completing the square, the value of x that produces a maximum or minimum function value on the given interval. Can you do this, guys? Complete a square here.
Yeah.
So Yusuf, you solve double I, Alan, you solve I, and I solve triple I.
Okay.
I start with triple I, and then I want you to let me know the answer. How are you doing, guys?
I was gonna ask you, I forgot how to complete the square for this one.
How did you do it before?
Well, normally I'm used to complex trinomials. I would use those. But this one, it's just not working. Would it be like X? Hmm.
Wait, so first thing we do is to convert it into standard form.
Oh no, it's in standard form. I think he wants us to put it in vertex form.
So we use completing the square.
And that's what it says. Complete the square and find the value of x that produces a maximum or minimum
okay.
function value.
Okay.
So what would you do?
You could use that formula x equals negative b over 2a to find the x value of the vertex, and that's your answer.
But you see, you have a range. Maybe your vertex is not in this range.
Then it's not the vertex.
But what would be the value of x in this case for vertex? Or y?
X equals negative b, so it would be negative 6 over 2, negative 1. Be
So it's
6.
gonna be 3.
That'll be 6.
How is the negative 6 over negative 2 equals 6?
It's not negative 2.
You 2
Oh, 2 times. Yeah. Oh, it is. It's gonna be negative 3. Yeah.
no, it's gonna be 3.
Negatives on the top. The bottom is 2a. Yeah, 3. Because they're negative.
I think I got it.
So and 3 would be the value of what, y or x?
Oh, that would be the x value.
You sure?
Yes, positive.
Okay. The way I would check it.
Oh, but you want to find the y value. So you want to plug in that value you get back into the formula to find the y value. So you sub in 3 to
Yeah,
get
3.
y value. So it would be
So you plug in 3 and you get 0. Or no, you get negative 9 plus 18 is going to be positive 9 minus 3 or 6, right? It's going to be equal 6. But you see that we have upward looking parabola, right? And you can see that the range of x is from 0 to 5.
yeah.
Yeah.
So you would be to the left side from value 6. So you would be on the decreasing part of the parabola, right?
Yeah.
And what would be the greatest value?
5.
No.
Oh, wait. The value of x produces the max or min value given on the interval.
So
Oh, wait, what is it asking us?
for each of the following function determined by completing the square, the value of x that produces a maximum or minimum function value on the given interval. So if this upward looking parabola and we come from left side. So for theoretically on the farthest point to the left, it should have the greatest value, right?
Yeah.
But if we plug in 0, we see that this is equal -3.
Yeah,
And if we plug in 5, we see that it equals +2.
yeah. Okay. So. Is it 2?
-25 plus 30 is going to be 5 minus 3.
Yeah.
Looks right to me. So I think you did some mistake. So are you sure that 6 is x value?
That's the Y value.
That's the y value. Okay. And what about x value in this point?
3.
So it equals 3. So this is 6 and this is 3,
Yeah.
right? And range is from 0 to 5. So we're actually in the range.
Okay.
0 to 5.
The parabola is wrong too, by the way.
Pardon?
The parabola is wrong.
It's not looking upward?
No, it's negative, so it looks down.
Absolutely.
So
It's
like,
gonna be the greatest value.
Yeah.
so the first thing we need to do is factor out the coefficients for the one I'm doing, the second one.
So in second one, you can use the same approach.
Yeah. So factor out
Um,
the coefficient of x squared.
No, just plug it into the formula. X equals -b over 2a.
Oh, okay,
but
okay.
it depends on what method of completing the square do you use.
Yeah.
So b equals -2. So you'd have 2 on the top, and then a is -1. So you would have 2 times -1. So it'll be 2 over -2.
Oh, okay.
-1.
Yeah.
Your x is -1, which means it's in range.
Yeah.
So it means it's in range, and it means it's either greatest or lowest point, right? If it's vertex of our parabola. But now, why would you use this scalar formula -b divided by 2a? Doesn't it seems like a bit too much to do?
There's easier way, then it's better.
There is an easier way. And now we're gonna learn how derivatives are making your life easier. Because if you find derivative for each one of these functions, and you find when derivative equals 0, you would find y value. Basically, you're gonna find x value of this point. So let's take a look at the first example. If we differentiate first one,
Is this the
I'm gonna
first-
get -2x plus 6, right? Am I correct?
Yeah,
Now I plug in that this derivative equals 0. So 2x plus 6 equals 0. -2x plus 6 equals 0. So x equals 3. Right? And that's what we found. Derivative would be tangent line to this curve, and it would be horizontal, or slope equals 0. Make sense? When derivative equals 0, it means slope of a tangent line at this point equals 0.
oh, wait, give me a second. Let me just copy it down, and then I'll maybe understand it.
So once you found x equals 3, next step,
Oh, okay, then you just set it equal to 0, and then you got x equals 3.
x equals 3, but to find y coordinate, I need to plug x equals 3 into initial function.
Okay,
No, not this one, but this one. And by knowing x coordinate, you already know position of this extrema, right? When you find when derivative equals 0, it means that you're looking for a point where tangent line is horizontal, and it's horizontal at point of extrema. Same for normal vertex, normal parabola.
Yeah.
Minimum value or minimum extrema would be at this point where tangent line has slope equals 0. Make sense?
Yeah.
And remember what derivative is. First place derivative defines slope of a tangent line to a curve.
Uh-huh.
So now you can find this vertex of your parabola not by using formula minus b over 2a, but by taking derivative of a function, finding value of x when this derivative equals 0, and for example, in advanced functions, if your derivative is quadratic function, for example, x squared plus 1, it would have multiple values when it equals 0, right?
Yeah.
But in this particular case, it would be 1 and minus 1. So these 2 points are going to be your extrema. Oh, sorry. No, sorry. X squared plus 1.
That's
Sorry, I'm wrong.
imaginary numbers. We haven't learned that yet. It's -1.
Yeah. So let me fix it. X squared minus 1. Okay. Now it's better. Now you see that you have 2 solutions.
Yeah.
And it means that your initial function, the one before this, the one before you differentiated, you see?
Mhm.
This function, for example, was third power something, because in this one we have second power greatest. And remember, derivative is always 1 power less than its prime function. You remember that, guys?
No, I don't think I remember that.
Remember that.
So never mind. It just implementation of power rule. If your power is n, derivative would be with the power n minus 1 or 1 power less.
Okay.
Make sense?
Yeah.
So what solutions for this when this one equals 0 is also solution for this when it reaches maximum or minimum values, as well as in this example. But here we have only one solution because derivative of quadratic function is linear function and it has 1 power. Power equals 1.
Mhm.
Can I clear the desk?
Yeah.
Yeah.
Please, Yusuf, read this for me and you're free to go.
Okay.
But one more thing before you run out from the class, you're gonna have home assignment for Thursday. Please do it. Yeah, I'm going to evaluate it by next Monday.
Oh, okay.
So read it, please, for me.
Oh, like read it right now?
Yeah.
Mhm.
Okay. The maximum point of a function that has a derivative of all points in an interval occurs at a peak fc equals 0, or at an endpoint of the interval
F prime of C, sorry. F prime
prime
of
of
C.
c, yeah, or at an endpoint of the interval. The minimum value occurs at a valley f prime of c of 0 or at an endpoint. This is true. This is true no matter how many peaks at the values of the graph in the interval. In the following three graphs, the derivative equals 0 at 2 points. And these are the graphs.
Yeah, now you see what I meant.
Yeah.
Yeah,
So for these cases, you're gonna have your two axes. So solutions of the quadratic functions would be here. These 2 points of x, x1 and x2, is when derivative of this function
equals 0.
equals 0.
Okay,
Same one for this. And same one for this.
okay. I see it better now.
And also you have minimum and maximum values of x. You see it? They are defined by the domain of a function or its range from x1 to x2, for example.
Mhm.
X1 would be the greatest or smallest, and x2 would be the greatest.
Mhm.
One more thing to note down before you leave. Algorithm. Please write it down briefly in your copybooks.
I'll take a picture of it. Later.
Yeah, me too.
You got it?
A picture of it, yeah.
Yeah.
So, Hoda, do you have any questions? Okay. So, guys, thank you for the class. Thank you for your attendance. We did a great job today.